Good afternoon, everyone.
Yeah, we can start now.
Yeah, okay. Good afternoon, everyone. Uh, so, how many of you have seen some number theory,
Yeah, sir, before we
like
proceed, I would
Congress?
like the host of the day to
Yeah,
introduce you.
Yeah. Firstly, we will
sure.
introduce you. Yeah, and then
Yeah, sure.
yeah. So, good afternoon to all of you. Welcome to the third event of Career Leave Days 2024. It is truly a privilege to introduce our esteemed speaker, Dr. Jay Mehta, who will be delivering the invited talk in this session. So, Dr. Jay Mehta is an assistant professor at Sardar Patel University, Gujarat. Also, he is an MTTS alumni. So, we are very happy to have sir with us today. So, a warm welcome to you, sir.
Thank you, Jyoti.
Yeah.
Yeah. So, is there anybody who has not seen number theory at all? Some basic congruences or something? Okay, let me start from the beginning only. So, let me share my screen. Yeah, I hope you all can see the screen.
Yeah.
Yeah. So before we see what is RSA and how do we test whether a number is prime or not, let us see some basic preliminaries. So all of you may be knowing about the congruence, right? When say m is an integer and a and b are integers, we say that a is congruent to b mod m. Right? We write like this, and we speak a is congruent to b mod m if m divides a minus b. So for example, 7 is congruent to 2 mod 5, right? Or 7 is congruent to 12 mod 5 or 17 mod 5, right? Because 5 divides the difference. Uh, Now there are many properties of congruences. Like we have A1 is congruent to A2 mod M, and we have B1 is congruent to B2 mod M. And we can add these two congruences, subtract A1 plus A2, sorry, A1 plus or minus B1 is congruent to A2 plus or minus B2 mod M, just using the division, right? Uh, Definition of congruence property, division. But one interesting property is this. We have, suppose A is given, A is an integer and M is greater than or equals to 1, then A has an inverse modulo M. That means there exists an integer B such that AB is congruent to 1 mod M if and only if GCD of A and M equals to 1. So A and M are relatively prime. Then it has an inverse. So it is if and only if. So A and N is relatively prime to M, then it has an inverse. If it has an inverse, then the GCD of A with M is 1. So we also often, if you have seen some group theory, you denote this by UM also. This is a group. This is a group of all integers, positive integers, which are less than equals to M, and GCD of K and M equals to 1. We know that this forms a group. If you take any two numbers, the product also is a product of two numbers also belong to UM. Again, one is the identity element, and inverse also is satisfied using this property. Okay. But if we take M equals to P, so P is a prime, right? Then we denote it by, we know ZP. ZP is this integers modulo P. 0 to p minus 1. And then this zp star. So then these are, because p is a prime, then all the positive integers less than p, they are relatively prime to p, right? And the GCD is 1, and so they have an inverse. So these are all invertible elements. So we often call ZP is a field, right? ZP is a field with p elements, right? All non-zero elements have an inverse. And you must also have seen Fermat's little theorem. Does anybody know Fermat's little theorem? You can use non-verbal feedback also in Zoom. Yes or no, you can raise hand or you can unmute and tell Fermat's little theorem. If p is a prime and a is an integer, then what is a power p minus 1? Can anybody tell what is a power p minus 1?
So
Yeah, Dhruv. Yes.
congruent to 1 mod p.
Yes, this is congruent to 1 mod p, but there is a condition. If p does not divide
A.
a, yes, if p divides a, then it is 0 mod p, right? If p divides a, then a is congruent to 0 mod p. P divides a, p divides a minus 0. This implies a is congruent to 0 mod p. So then it is 0. So this is a property of primes. So if p is a prime, then for any integer, we have a power p minus 1 is either 1. If p does not divide a, then equivalently, that means GCD of a and p is 1. And if p divides a, then it is 0. And so this is, if some of you know group theory, is a bit of group theory, then this is a cyclic group under multiplication modulo n. We may not use all these things, but just because we are discussing this. Right, so this is Fermat's little theorem. We call it version 1. Okay, now so what is order of A? The order of A is the smallest integer such that, so your order of A is k, then k is the smallest, of course, smallest positive integer, such that a raised to k is congruent to 1 mod p. Okay, and if a raised to n is congruent to 1 mod p, any power of a gives 1 modulo p, then order of a divides n. And in particular, by Fermat's little theorem, order of a divides p minus 1, because for n equals to p minus 1, this is true. It is 1 mod p, right? Okay, so now comes the problem. So RSA is based on this problem. So we have a congruence. So E and C are integers. And we have a congruence. X power E is congruent to C modulo P. So modulo P is just, we are dealing in modular arithmetic. So we are reducing everything modulo prime P. Right? So suppose we have such an equation. Let's say X power E is equals to C. So how do we solve this? We need to find eth root of x, right? So if we have x square equal to c, so what we do, we take square. So this is c power x will be c power 1 by 2. So here also we need eth root. So we need inverse. If I want to find value of x, then x is nothing but I can apply the power E inverse, then this is nothing but, right? So we need to find this. What is 1 upon E? 1 upon E, but that is E inverse. And when does inverse exist? So this is just we have seen. When does inverse exist? So inverse exists if they are relatively prime. So inverse modulo what? So A has an inverse modulo M, right? A into B is such a B exists. AB is congruent to 1 mod M if and only if GCD of A and M is 1. So here we need inverse of E, but E is in the power, right? And by Fermat's theorem, just now what remark we had made, this power, right? This is dividing P minus 1. So the inverse we need modulo P minus 1. So when does this exist? So the proposition says that if GCD of E and P minus 1 is 1, then E has an inverse modulo P minus 1, say D. So that is ED is congruent to 1 mod P minus 1. And then this congruence, this is the congruence which we are interested in. Then the congruence X raised to E is congruent to C mod P. It has unique solution. And is given by X equals to X congruent to unique solution modulo P, of course. It is given by, we take the inverse of E on both sides. So inverse of E is nothing but D. So C power D mod P. This is a solution. So if we have a congruence like this, X power E is congruent to C mod P, then if you want to find the solution, this condition is necessary because we want inverse of E, and we can raise to the inverse of E on both sides to get the solution. So if this condition is dropped, then the result may not be true. We may get solution in some cases, we may not get solution in some cases. And even if we get solution in some cases, it may not be unique. So to get the inverse of E, it must be uh, relatively prime to P minus 1. I hope it is clear. I'm not going too fast. If I'm going too fast, just let me know. Okay, if you have any doubt, you can just ask me. Unmute and ask. And okay, the proof we are not going into, but what it uses. So proof uses Fermat's theorem that we have seen. Simple application is just we have to verify. Everything is given. We have to just verify, plug in the value of X in the congruence C power D. So you have C power ED, and ED is nothing but it is 1 mod P minus 1. So ED is of the form 1 plus K times P minus 1. And anything raised to P minus 1 modulo P by Fermat's theorem is 1. So you'll get C. So the congruence is satisfied. The proof is very simple. Okay. Now the question is, can we generalize this for 2 primes? Okay. Here we have only 1 prime P. And now the question is, can we generalize this? So suppose we are given congruence X power E is congruent to C modulo PQ, where P and Q are distinct primes. Okay, so P and Q are distinct primes. And now we want to find out the solution. So again, for this, we need again the condition that GCD of E, because again we want inverse. But now GCD of E with what? So we are taking modulo PQ. So again, generalization of Fermat's theorem, that is a question. A power P minus 1. So can we have A power P minus 1, Q minus 1 is congruent to 1 mod PQ? And yes, that is true. In fact, a power p minus 1 q minus 1 divided by g, where g is nothing but GCD of p minus 1 q minus 1. This congruent to 1 mod pq. Using that, we can conclude that, again, just like previous, if GCD of E with p minus 1 and q minus 1 is 1, then it has an inverse. There exists B such that ED is congruent to 1 modulo p minus 1 q minus 1. And if it is an inverse, then we can find the solution. We can just take the inverse of E on both sides. Then the congruence x power E is congruent to C modulo PQ as a unique solution again, given by x is congruent to C power D modulo PQ. Okay, so first congruence we had just seen modulo P, and now this is modulo PQ. And this does not use Fermat theorem, it uses this, a generalization of Fermat theorem. Of course, we know Euler's theorem, but this is called Euler's formula for PQ. So using Euler's formula for PQ, we can prove this. So this property is used in RSA. I'll tell you about RSA. So there are two types of cryptography. Cryptography basically is a science of secret writing, right? Confidential message information we want to pass from one party to another, uh, so that no other adversary or no third party can read our message. Not only confidentiality, this is the primary goal. Uh, its secrecy is there, and then authenticity, everything is there in cryptography. So that science is basically called cryptography. And there are two types of crypto systems. So that one is called a private key, which is called symmetric key cryptography or private key cryptography. Another one is called public key cryptography, or which is also known as asymmetric key cryptography. So what happened in private key before 1970s? Private key cryptography was very much in practice and popular, but private key has certain drawbacks, some disadvantages. For private key, if I want to communicate with each and every one of you, I need uh, to use so many keys, different keys for each and every one of you. So too many keys I have to handle. And then there is again authenticity is a problem. So public key came into practice after 1970s. Public key, there is only one key. It's just like an email address. So that is public to everyone, my email address. And my private key is nothing but it's my password. So those who want to send me message, they can send me like an email using my public key. And only the one who possesses private key can only read the messages, encrypted messages. So just basic overview of cryptography. Now RSA is a first popular public key crypto system. Uh, the name is based on the three people who proposed: Rivest, Shamir, and Adleman. So it was proposed in 1977 publicly first. It was proposed by these three people, and that is why it is named. So this is also known as RSA PKC, Public Key Crypto System. Okay, now let me tell you what is RSA. So if you have seen any cryptography lecture, or if you read any basic book on cryptography, you will see these two parties. One is Alice and one is Bob. So they want to communicate with each other. And then there is another eavesdropper, a villain, a third party who wants to read their messages, wants to find out their key and break their crypto system. That is Eve or Charlie, or many names are used. So what is RSA? RSA, suppose Bob wants to receive the messages. So Alice wants to send a message. So Bob will generate first his uh, public key. So what Bob does is Bob chooses two large primes P and Q, and then he computes. Okay, and then he chooses an integer E such that GCD of E with P minus 1 and Q minus 1 is 1. So this Bob starts with two very, very large primes, so many digits, not just one we use in practice. So there can be hundreds of digits. So it's like maybe 1,000 bits, so 300 digits prime. So then the question comes how to generate those primes and whether how to test. So that's one part of our talk, that how to test whether a number is prime or not, which will come later. So there are two things which Bob does. One is take two large primes, take their product n, and choose an integer e such that GCD of e with p minus 1 and q minus 1 is 1. And then he makes this pair public, n and e. This is called public key of Bob. Of course, primes are very secret. Nobody should know the prime, otherwise this algorithm fails. Everyone can break and see the messages. Now Alice wants to send a message to Bob. So Alice has a message, and message, we always have many ways of converting message in number. So we always consider message as a number. Um, and now how does Alice send this message? So Alice first encrypts this message. So all of you know basic cryptography, you know there is encryption. The data does not go in the normal crude form. It is converted into some junk or gibberish text which we may not recognize. That is called encryption. That is called encrypted text, and the process is called encryption. So she computes. She uses Bob's key. So she computes C equals to m power e. So Bob has two public key, E and two parts of public key, N and E. So E is the exponent, encryption exponent, because to encrypt the message, she used that. So E is called the encryption exponent, and N is called the modulus. N is nothing but P. Okay, and now she sends C to Bob. Okay, and all this is in open channel. So Eve knows all this. Eve can trace this. Of course, Eve knows public key. It is known to everyone. Eve may be smart to trace C from Alice when it is going through an open channel through Bob. To Bob. Okay, now Bob, what Bob does? Bob computes M dash, which is C is received. So to compute M dash, first Bob has to compute the inverse of E. Right? So this is M power E. How does one extract M? So just like this, uh, same as this problem. If you have a congruence x power e, what is the value of x? Just take the inverse of e. When does inverse of e exist? If e is relatively prime to the product p minus 1, q minus 1. Right? So Bob computes the inverse of e first. Bob computes d such that ed is congruent to 1 modulo p minus 1, q minus 1. So he computes first the inverse and then takes t power d modulo n. N is nothing but pq, same as what we had seen previous. So this is nothing but c is m power e d mod n, and m power ed is nothing but m. So this is how Bob gets the message m. Is it clear to everyone? RSA is a very popular crypto system. Maybe you have. Okay. Am I audible? Jyoti, Chaitanya?
Yeah.
Okay. Because I got a message that my connection was weak in between. Okay, so no doubts here, then we can go ahead. So how does a third party or an adversary or a eavesdropper, what is her interest in finding the message. So how does she find the message? So she has to compute she wants m from this. That means she has to solve this congruence. X power e is congruent to c mod n. This is x. So if one wants x, one needs inverse of e. How does one find inverse of e? E is relatively prime to the product p minus 1 and q minus 1. So inverse of E exists if we know the values of P minus 1, Q minus 1. Then it is just a problem of finding the inverse, which is very easy. So now coming to the security of RSA. So how does one compute inverse? So for inverse, one needs P minus 1, Q minus 1. But we have to find D. Just like what Bob did. Bob just took C power D. So just E also needs to find D. How does she find D? D is the inverse of E. E is already public. So she has to find inverse, but she doesn't know P minus 1, Q minus 1 because she doesn't know P and Q. P and Q are private. This is just multiply. Okay. So what if suppose if she has P and Q, then she can find P minus 1 and Q minus 1. Then Eve can find this. If Eve can find this, then Eve can compute D such that ED is congruent to E is already known modulo P minus 1, Q minus 1. So that means if Eve can factor n equals to PQ, if Eve can factor n and find the primes, then Eve can find the message sent by Alice to Bob. On the other hand, Eve does not need to know P and Q. Eve just needs to know P minus 1, Q minus 1. But it is the same. Why it is the same? So suppose Eve knows P minus 1 and Q minus 1. Then she can take the product P minus 1, Q minus 1. And this is PQ minus P plus Q plus 1. PQ is n, which is already public. So Eve knows this. So if Eve knows the P minus 1 and Q minus 1, then Eve knows P plus Q. So if Eve knows PQ and P plus Q, then she can just compute this, roots of this equation. And this is nothing but, so that means Eve knows P and Q. So both are equivalent. So actually Eve wanted to find D. To find D, you needs this P minus 1, Q minus 1. So one way is that you can factorize and find the primes. Then find P minus 1, Q minus 1, find the inverse, and then just like Bob, find the message. So factorization was the one way. But Eve needs only this. But it is equivalent to factorizing n only because if one knows P minus 1, Q minus 1, then one knows the product. One already knows the product of PQ, which is n public key of Bob. So one now knows the value of P plus Q. Then just P and Q are just matter of solving this quadratic equation. So both are equivalent. So finding P minus 1, Q minus 1 or finding P and Q, they are equivalent. So security of RSA relies on factorizing n. So there are two major problems. One is called the discrete logarithm problem, which we are not discussing in this talk, and one is factorizing. So factorizing a product of primes. So our difficulty of RSA is based on this. Okay, but the thing is, however, uh, Eve does not need to factorize also. Eve just want to find the value of m. So Eve needs to solve this congruence. X power e is congruent to c modulo pq. But so far there is no other way known other than factorizing n. So that's why the problem has come down to factorizing n, which is one of the difficult problems. Believe it's not impossible. There are ways, or there are some primes uh, which will lead you easily factorize the product, which we are not going to see it. So now there are two questions. One is from EU point of view, how to factorize n to break the RSA, and from Bob point of view, how to generate these two primes to uh, implement RSA. So for RSA, one has to generate two large primes. So these are the two things now comes from RSA. And this one once maybe a couple of decades back, this was a very popular problem. There was a website with the name RSA, and it displayed all these values of n, different values of n with a different prize money. It was, I think, by some USA website, which was called RSA, and it has even $1 million problem. So it depends on the difficulty level, the price depends on. And the one who factorizes is they get the award, and they discard those primes, those modulus, and the one and the those n which are not factorized, they use in their security purpose. Just a couple of decades back when I was doing my PhD, at that time this was very popular, but now it has stopped. Okay, so now the question is from Bob's point of view. We are not going to see Eve's point of view, how to factorize. There are many methods. One of the popular method is Pollard's P minus 1, which we study in cryptography if we study in detail, but how to generate large primes. So far, is it clear? Or do you have any doubts in this? I have 1 hour, no? So total 1 hour session.
Yeah, 1 hour, 15
Yeah.
minutes.
Okay.
With
Yeah.
Q&A, yeah.
Okay. So I hope so far it is clear. Okay. So now suppose Bob has this number n. So this is such a big number. This is how they check. So how many primes are there? How to generate primes? Again, that is probabilistic question, which uses prime number theorem. We are not going to that. But suppose Bob has chosen a large prime, a large number. So Bob has taken care of that. It is not divisible by smaller prime factors. So Bob has checked. And but how does Bob know that whether this number is actually a prime or not? So Bob needs two primes. For n equals to p q, Bob needs two primes, p and q, right? So if so, this is say p, right? One, but whether there is a prime or not, how do we check? Of course, we can check the divisor. If it is divisible by some prime, then it is a composite number. It is not a prime. But this number does not have any divisor. Uh, Less than 10 power 6. So 1 million. So up to 1 million, there are no prime factors. So how does one then check whether the number is actually prime or not? Because Bob may believe that this number is prime, and Bob may use this as P and generate another such number as Q. And then it may happen that they may not be prime, and you may be able to factor and find the message. So then we need some property of primes to test whether number is prime or not. So this brings us to uh, because more than this divisors also it is not possible to check. I mean, not saying not possible, it becomes more difficult to check divisors. We cannot go up to root n. Our trial and error method, what we do in school, if we are given a number n, if we want to check whether it is prime or not, something like this, right? What do? We take up to root n. So there's like 1,000. So we just go up to 30 or so, and then we check the primes up to 30, up to root n. If it is not divisible by any of the primes, then number is prime. If you have found a prime factor, then number is not a prime. But it is not possible in such a large number. It's not easy. So one is the test which is due to Fermat, which we have seen Fermat's little theorem. A power p minus 1 is congruent to 1 modulo p if p does not divide a, that is GCD of a and p equals to 1. And this is 0 mod p if p divides a. And then we can multiply in the first case. If p does not divide a, then we can multiply a both sides. So we have a power p is congruent to a modulo p. And what about the second case? The second case, p divides a. If p divides a, then a is congruent to 0 mod p. Okay. Then, so right hand side is 0. A is congruent to 0 mod P. What about the left hand side? If A is 0, A power P is also congruent to 0 mod P. So then also this is true. So in both the cases, this is true. So now this is true for all integers. And this we call Fermat theorem version 2. So what the statement is? The statement is if P is a prime, then P is a prime implies given any integer A power P is congruent to A mod P. Okay, so what Bob will do? So here Bob has this number n. So Bob will choose A equals to 2. And Bob will compute A power n. Right? And if it is not congruent to A mod n, so 2 power n is not congruent to, 2 mod n. So powering is easy, right? There are many algorithms which compute powers in very quicker way. So 2 power n, if it is not congruent to 2 mod n, then Bob knows that n is not prime. Then Bob can discard this and choose another number. So this, what is a contrapositive of this? This says that, if P is prime, this implies given any A in Z, A power P is congruent to A mod P. So if there exists if there exists an integer A such that A power, so here now let me write n is prime, then this. So A power n is not congruent to A mod n. Then n is composite. Right? This is not if and only if. So note this. There's only one side. If P is a prime, then given any integer, A power P is congruent to A mod P. If A power P is congruent, so if I take A equals to 2, 2 power n is congruent to 2 mod n. I cannot conclude that n is prime. Does not say that. If it is prime, then this is true for every integer. Okay, but suppose this is not true, then certainly this is not prime. So if this is a large number and we raise it to the power 2, 2 power n does not give us back 2 modulo this number n. That means n is not prime, because if it were prime by Fermat's little theorem, it should give us 2. Okay, so one test is by Fermat, this is called Fermat's test, and which is this. And in this case, A is called a witness for the compositeness of n. A is called a witness for the composite because A has given a proof that our number chosen n is not prime. Because if it were prime, A power n must be congruent to A mod n. But if we found an integer A such that A power n is not congruent to A mod n, then definitely n is composite. And what Bob does is that discard that number and choose another number, large number, and then again check. Is it clear? The test is one side only. If this condition holds for some A, then we cannot conclude that it is prime. Okay, but now the question is, what happens if I choose all the A and this condition holds? So can I say that the converse is true? I'm repeating again. What happens if I'm not able to find any witness? Okay, for example, I know 22 is not prime. So how do I conclude? I'll check 2 power 22. Will it give me 2? Then I cannot say anything. If it is not giving me 2 modulo 22, then I have a 2 is a witness. 22 is not a prime, because if it were prime, this should be 2. A power p must be A. So 2 is a witness. If it is 2, I cannot say anything. I have to check for 3. 3 power 22. Is it 3 mod 22? If that is congruent to 3 mod 22, I cannot say anything. I have to check the next number. But if it is not congruent to 3 mod 22, 3 power 22, that means 3 is a witness. That 22 is not a prime. Because if it were a prime, this should be true for all integers. I hope this is clear. But what will happen if I start from a equals to 0? Let's 0 anyway, 0 power anything again 0. So that is true. For 1 also it is true. So let us start from a equals to 2. 2 power n is congruent to 2 mod n. Suppose we get this. 2 power n is congruent to 2 mod n. We cannot conclude that n is prime. If it was not 2 mod n, then definitely n is composite and 2 is a witness. So we check for 3. 3 power n is congruent to 3 mod n. We cannot say anything. But if it is not congruent to 3 mod n, then 3 is a witness for the compositeness of n is composite. Then we check 4. So if we keep on checking like this, and every time the test, it passes the test up to n minus 1. So 1, 2 to n minus 1. N minus 1 power n is congruent to n minus 1 modulo n. Suppose for all integers less than n, the test passes. And can we say that converse? If given any a power n is congruent to a mod n, can we say that a and n is prime? What do you think? Do you have any idea? Any? What is your feeling?
Sir, if we can't find a witness, we still can't say it is not a prime. Sorry, it is not a prime. We cannot be sure. It is a prime.
Still,
We
we
cannot
cannot be
say
sure because I mean, not a prime or composite or prime, we cannot say, right? Because the converse is not true. But still, like if this is, we cannot find witness. Bob doesn't find witness. Bob is tempted. Like this is a very high probability that number is prime. Because if it were not prime, then we can find a witness. But that is not true. And that such number are called Carmichael numbers. So what are Carmichael numbers? They are composite numbers having no witness. So it was first, I think in 1910 or 1912, R.D. Carmichael, he published a paper in American Mathematical Monthly. The reference is given, link is also given, and he said that there are composite numbers uh, which give no witness. For example, one is 561. 561 is the first Carmichael number. He listed 15 such numbers. They are called Carmichael numbers. So 561, this is composite number 561. You can see that this is divisible by 3 and 11 and 17. Right? 3, 11, 17. Let me just check. Yeah, 3, 11, 17. 561. This is a composite number divisible by 3. You can just check the sum of the digits. Right? It is 12. So it is divisible by 3. But you take a equals to 2 up to 560 and we check a power n, a power 561. A power 561 is congruent to a modulo 561 for all a. So it does not have any witness. So then the problem is that what if Bob chooses a large number? Bob thinks that it is a prime, doesn't find a witness. Okay. But then there are Carmichael numbers. So what Bob think up to this time? Okay, there are 15 such numbers listed. But this was in 1912. And later, after 8 decades, uh, these were the 15 numbers. One interesting number is this 1729, Ramanujan's number. Right? So this is 3 into 11 into 17. And this one is this anyway, it's divisible by 5, we know. But again, this does not give any witness. And this is, we know this is Ramanujan's number, right? Taxi cab number. And this is also composite number 7 into 13 into 19. But this does not give any witness. That means A equals to 2, 3 up to 1728. And we have A power 1729 is congruent to A modulo 1729. It's a very interesting number, and probably this was anyway in Carmichael's paper 1912. It was given before the death of Ramanujan, but maybe he may not be knowing it at that time. Otherwise, he would have told Hardy about this property also. We already know it can be expressed as sum of two cubes in two different ways. But then it is the third smallest Carmichael number. The first one is 561. So for this, there are no witness. And these are the 15 numbers, some numbers listed by R.D. Carmichael. But then in 1994, Alfred Granville and Pomerance, they published a paper in which they proved that there are infinitely many Carmichael numbers. Now the trouble for Bob increases because there are infinitely many Carmichael numbers, and Bob chooses a very large number, many digits, which does not have prime factor up to say 1 million or let's say 10 million. Then how to conclude that it is actually a prime or it does not have any prime factor more than that also? So if Bob uses Fermat's test, then there is a possibility that Bob might hit upon a Carmichael number. He may not find a witness and he thinks the number is prime. But when he uses in the RSA algorithm, and he might be able to factorize it using some other method. So there are infinitely many Carmichael numbers. So this makes Bob want to use a better test for primality. Right? Fermat's test doesn't work. Fermat's test says that a power, if p is prime, a power p is congruent to a mod p for every integer a. So the test uses contrapositive of that. If there exists an integer a such that a power n is not congruent to a mod n, and then n is composite, and Bob can discard it and use the next one. But that doesn't work because it has Carmichael numbers. Those who know a bit of programming can check that all these are Carmichael numbers. I made a Python program and then checked that it does not give any witness. So now coming to another test. So Miller and Rabin. So in a separate paper, they have uh, given a property of primes, and that is another alternative to Fermat's test, which is again better. Why it is better and what is the property of the primes? So this is the property of prime. Like in Fermat, p is a prime. Then for every integer a power p is congruent to a mod p. Here, uh, if p is a prime, of course, odd prime we are taking, and then write p minus 1. P minus 1 is even. So we can write p minus 1 as 2 power k times q. You extract all the powers of 2. So maximum powers of 2 are, let's say, k. P minus 1 is even, so k is greater than equals to 1. And q remains now odd. Q is reduced to an odd number. So p minus 1 we write like this. Then what does Miller-Rabin property says? Then one of the following holds. So either for every integer a such that p does not divide a power q, a power q is congruent to 1 mod p. Okay, so if p is a prime, then if we write like this, then a power q is congruent to 1 mod p. Either this holds or one of the following numbers is congruent to minus 1 mod p. What are these numbers? Start with a power q, then square it. So a power 2q, then square it, a power 4q, then a power 8q, which we can write 2 power 3q and so on, up to a power 2 raised to k minus 1 times q. One of them is either congruent to -1 or the first one. So if we combine these two, then it says that the first one, a power q, that odd part, is either 1 or -1. Either this or rest of the others, one of them is -1. Proof is very simple because proof is just, you can discuss in one line. Make this list: a power q, a power 2q, a power 4q, and so on. And you have this a power 2 raised to k minus 1 q. What will be the next number? Again, we square it. So we have a power 2 raised to k times q. But 2 raised to k times q is nothing but p minus 1. So this number is actually a raised to p minus 1, which we know by Fermat's little theorem. This is 1 mod p. So last one is 1. I've added one number, which was last one. So last one is 1. And how do we get all these numbers? So we get all these numbers by squaring the previous one. We start with a power q, the odd part of odd factor of p minus 1, and then we square. In last number we are getting 1. So then there are only one of these two possibilities. The first one is 1, and then we square and we get all as 1 1 1 1, such a sequence. So then this is satisfied. Okay, if the first one is not 1, that means some number is not 1, but when you are squaring, at some point of time you are getting 1. Either here, then this square is equals to 1, or somewhere here we are squaring and we are getting 1, and rest sequence is 1. So then some number which is not 1, but squaring it makes 1, that means it must be -1. So one of this must be -1. The proof is simple. I hope this is clear. Very nice property, just like Fermat's property. Okay, so p is a prime. Then write p minus 1 as this. Then take the odd power. Either it is 1 or this sequence up to a raised to 2 power k minus 1 times q. One of them is -1. So what happens? Again, this, if p is a prime, then all this, one of this is true. So again, use the contrapositive of this. If that means if this is not true and none of this is congruent to -1 mod p, then we can definitely say that p is not prime. Okay, so this gives us Miller-Rabin witness. That was Fermat witness. Now what is Miller-Rabin witness? An integer a is said to be a Miller-Rabin witness for the compositeness of n if, so if n is prime, then one of them is true. So if none of them is true, then n is not prime. So if a power n is, so write n equals to not a power n, but we write n minus 1. We write n minus 1 as 2 power kq. So if a power q is not congruent to 1 modulo n, and none of those numbers, a power 2 raised to I times q is not congruent to -1 modulo n for all I equals to 1 up to k minus 1. If both are not holding, then n is composite and a is called a witness. This is called a Miller-Rabin witness because now we are using this Miller-Rabin property of primes. Okay, so is it clear? So, but then how this property is different and why it is different, better than the Fermat's test? So because there are no Carmichael like numbers in Miller-Rabin test. So there are So Carmichael numbers were the composite numbers, but which were passing the test. So here we don't have any Carmichael like numbers. That means this is not going to be true for all A. If the number is composite, then we'll be able to find a witness. So if we don't find a witness, we are certain that the number is prime. In fact, not only that, there are 75% of witnesses. 75% of Miller-Rabin witnesses. So if you have 560, 561, this was Carmichael number, if you remember, the smallest Carmichael number, which did not admit any witness, yet it was composite. So there are 75% of witnesses. That means, let's say 560, if we say, then 3/4 are the witnesses, only 1/4 of them. So 140 may not be witness, but more than, so 560 minus 140, that is 420 witnesses are there. So there are high chances if I start with A equals to 2 and use this property, then I may get a witness. If 2 does not satisfy this, 2 satisfies this property of Miller-Rabin property of primes, 2 is not a witness, I can move to 3, I can move to 4, but there is a chance that I'll find a witness because it certainly does have a witness. And 3/4 of the numbers from 1 to n are the witnesses. So let us just, before we conclude, let us check how does 561 gets caught up here. 561 was a Carmichael number. It passed Fermat's property for all the numbers, for all integers A from less than 561 up to 560. So, but here we take n equals to 561. What we do is n minus 1, 560, which is 2 raised to 4 into 35. So our k is 4 and our q is 35. Okay. And so what we check A equals to 2. Let us check A equals to 2. Whether 2 is a witness or not. Of course, 0 and 1 will not help. So what will be 2 power 35 modulo 561? So let me just tell you the numbers. So 2 power 35, if we compute, it is 263. So we know A power q is congruent to 1 mod n, or A power q, A power 2q, A power 4q up to A power 2 raised to k minus 1 q is congruent to minus 1 mod n. One of this. So the first one is not 1. So this property is not satisfied here. What now we have to take, now we have to square this. So 2 raised to 35 square, which is 2 raised to 2 into 35, which is 263 square, and 63 square is 166 modulo 561. All this can be computed using square and multiply method, fast powering algorithm, which we also call using programming. This can be done easily. So this is not minus 1. So the first one is not even 1 and not minus 1, and then again square. So a power, 2 power 4 times 35, which is 166 square, which is congruent to 67 modulo 561, which is again not minus 1. Again we square till k minus 1. So k minus 1 is 3. So 2 power 3. So this is 8. And so 67 square, which is congruent to 1 modulo 561. Again, this is not minus 1. Not minus 1. That's it. We are done. So first one is not 1. And all this squares up to k minus 1, they are not minus 1. So then that means 2 is a witness. We have found the first one. We selected 2 and 2 is a witness. We take a equals to 3, 3 is also witness. So there are 75% of witnesses are there. So you can check all these numbers Carmichael numbers which we had seen, which pass the Fermat's test, right? Here, all these numbers, for all these numbers, including this, a equals to 2 is a Miller-Rabin witness. First number itself which we choose. We, of course, we have to choose randomly. We can choose anything, but a equals to 2 gives a witness. Using programming, I checked. This is the first number where a is 2 is not a witness. It is not a Miller-Rabin witness. For this one, I got a equals to 3. Again, here a equals to 2 and all this. So this is how Miller-Rabin test is very efficient uh, in testing whether number is composite or not. Right. So finally, one question. So this is nothing, no research work on anything, but just I started working in cryptography when I was in PhD before I shifted to number theory. Then I wrote my thesis, on number theory. But then again, for past 2 years, I'm teaching this course in the MSc in my university. So this is the course I'm taking, and this is one of the topic which fascinates me. And this is the question which I have in mind. It's very vague question. I don't have any idea about it, but then like what are the properties of primes? If there is any other property, that can be. So there are many properties of primes we study, right? But I have not thought about it yet, but this is just a question in my mind since last semester. Like Fermat property is there for primes, and then you have Miller-Rabin property, which can be used for primality testing, and which has very many applications in many branches, but of course, especially in cryptography. So, are there any properties of primes which we can study? In whenever we see some property of primes, we can ask a question that if this is not satisfied, then we know that number may be a composite. Are there Carmichael-like numbers for such a property or not? That can be explored. That is one question. And this is the text which we are using in our semester course, An Introduction to Mathematical Cryptography by Hofstein, Pfeffer, and Silverman. And I have written some programs, Python codes. Of course, code is not there on the website, but for my students to check whether they are computing, when they are computing the numerical questions, so whether they are getting correct values or not. So they are given on my website. The link is also given there. Okay, so I stop here. Are there any questions? Purnima has a question that are there any loopholes in the Miller-Rabin test similar to what we had in Carmichael numbers? Not that I know. Book says that no, there are. The problem is what happens if we just randomly test a number and we don't find a witness? So then we look for another number. Then we look for another number. So if our number is so large, of course, we are not going to get a witness so easily. But then, with every attempt of not finding a witness, the probability increases because we know that only 1/4 are non-witness, 75% or 3/4 are witness. So 1/4 is a probability. We attempt again. So 1/4 square. Suppose we get 10, we attempt 10 values of A, and all the 10 are not non-witness. That means our probability is 1/4 power 10, which is 10 power minus 6, approximately 10 power minus 6. So that means 10 values we are not getting a witness. Then we try another 10 values. So if we try 100 values, then the probability of the number becoming prime is increases. So, but then there is till 2002, there was no such algorithm to test completely whether the number is a up to when we'll get a witness. What is the surety that up to this much range we find a witness? But it is a matter of pride for us that in 2002, three computer scientists from IIT Kanpur, Agarwal, Kayal, and Saxena, they proved that there is a polynomial time algorithm which determines witness. But then the process itself is very slower than the Miller-Rabin test. So what happens is if one tries 50 to 100 numbers and one does not find a witness, then one is ready to accept that the number is prime because of the high probability. But again, there are no Carmichael-like numbers. We'll always find a witness. And I have tried many numbers, Carmichael numbers, and always A equals to 2 is a witness. To find a non-witness, it is difficult. So you can imagine how many witnesses are there. As I said, 3/4 are there. Finding non-witness is difficult in that case. Of course, in some numbers, there may be many non-witnesses, smaller number. But then we randomly check the values of A. There is a high chance that we may find a witness, but no Carmichael-like numbers. Okay. Are there any other questions?
Yes, if audience have any questions, then you may ask here. Okay, so I guess we are done. So thank you, sir, for such an insightful talk. At the end,
Thank
we would
you.
like to have a group photo. So all of you can
Sure.
turn on your videos so that we can have